A variable lab bench power supply is one of the most important tools an electronics maker can own. It's mandatory while testing circuits because you can now limit the current. If something goes wrong during prototyping, then this means most things will not blow up anymore. You can also use it to charge lithium-ion batteries or reliably determine the forward voltage of a high-power LED. This list goes on and on. So in this video, I will show you how you can build your own very easily without making your own circuits. It's all modular. Let's get started. The star of this supply is this LTC3780 step-up, step-down converter. It combines an efficient and really powerful buck and boost converter for the price of $21 US. Let's test this thing before we put it in an enclosure. I connected my wire adapters with the power wires of my voltage current display to the input of the board. The output's positive connects to one loose wire and the voltage sense wire of my display. The black wire of my current measuring path connects to the negative output. This loose wire represents the positive voltage and the red wire ground. This configuration stays the same when the supply is inside the enclosure. Now I can turn on my bench power supply, set the voltage to 12 volts and connect the wires. Everything powers up and we can play with the 3 potentiometers. The far right one controls the undervoltage protection and is mostly used for solar charging. We do not care about that, so don't touch it. The far left one controls our voltage. The minimal voltage is not 0 volts, but it's very close with 0.8 volts. It's not a tragedy that we cannot reach below 0.8 volts, because such low voltage values are not that useful anyway. The maximum voltage is around 29.4 volts, so I would say it's a pretty neat range. The potentiometer in the middle can limit our current. The minimum is around 300 milliamps, which is still quite high for many circuits, but we cannot do much about it. The maximum current is limited by my display, which only endures up to 3 amps. But small peaks of higher current should not destroy it immediately. Now let's find out whether the built-on heatsink is enough for our project. I created this Frankenstein power resistor and soldered it to my output. If you are asking yourself right now, why am I placing the resistor on top of a glass of water, then just wait a second. I cranked up the voltage and shortly reached the maximum of my bench power supply. This means we need more power. I got this 12 volt 5 amp power supply, which should power quite a lot of things, with 60 watts of power. This supply uses a screw terminal, so I wired up my old school plug and connected the AC wires to the terminal. And if you have no experience with electronics whatsoever, then better buy yourself a variable bench power supply, because this AC voltage can kill you, so be careful. Now let's plug it in and set the voltage to exactly 12 volts. The supply connects to my board just like before, and now we can properly heat up the resistors. Right now I'm using around 60 watts of power with 29 volts on the output. And fair enough, there goes my solder connections. Now you know why I used the glass of water. I did this before without it and got a nice burn mark on my table. Because I'm such a genius. The heatsink, on the other hand, just warmed up a little bit and definitely does not need to be beefed up. This is basically the whole structure for the supply, all just simple wire connections. So let's take a look at the enclosure. I went with this grey beauty which even has ventilation slits. The front and back panel are made of metal and will make this look awesome in the end. Additionally, I also used an AC input, an AC switch, 2 binding posts, 2 potentiometers with knobs, and a couple of screws. A parts list and more pictures are as always on Instructables. Firstly, let's replace the 500 kilo and 200 kilo potentiometer of the LTC3780. I just heated up the pins of the pots and shortly after they fell out on their own. Afterwards, the shaft of the new potentiometers got shorted with my rotary tool, because the knobs would otherwise stick too far out when mounted. Then I soldered 3 wires to my new pots, added shrinking tube and soldered those wires to the solder joints of the old ones. Now I covered the front and back panel with white tape and did some basic measurements where I want my external parts to be placed. I marked those spots and used a drill to make small holes which I could enlarge later to squares with my saw or bigger holes with my drill again. It took quite a lot of patience to make those cutouts look good, but it worked out somehow. Okay, time to mount the parts. Nothing special to say about most of them. But it is very important that you make sure your binding posts are isolated from the front plate. And make sure that your protective conductor of the AC input has a proper connection with all metal parts of the enclosure. I drilled small holes for this and secured the wire with a nut and a washer. Please don't forget that. It's an important safety feature. Now it's time for the other wiring. The AC input connects to the main switch, which then connects to the input of the 12-volt supply. And I'm using flexible 2.5 square millimeter wire, if you are curious. All the other wiring is the same as before, except for the binding post, which connects to the positive output of the LTC 3780 and the red wire of the current path of the display. Now let's secure everything with screws and hot glue. Close it all up and we are done. Like I said, super useful and with a maximum of 6 amps, much more powerful than my other bench power supply.